Okay, so we talked about diode rectifier circuits in the previous few videos, right? And we saw that one of the limitation that those circuit have is output voltage is uncontrollable, and what we mean by that is that output voltage certainly depends on the input AC voltage, but then it cannot be controlled by an external trigger or an external signal, right? So therefore, in certain applications, for instance, when you, let's say, want to control the output voltage, which can then be used to control the current that is flowing in the armature winding of DC machine, thereby, let's say, you want to manipulate either speed or torque, you cannot do that unless you include another kind of a transformer, which is also known as auto transformer, wherein you can have multiple tappings, right? And then you can adjust the input voltage. But the transformer, as we understand, are usually bulky and inexpensive, right? And therefore are not really the preferred choice of manipulating the output voltage, although that solution was popular before, but then with the arrival of thyristor circuits and with the popularization of thyristor circuits, these new generation of circuits came up. Now, when I say new, again, it is something which I'm referring to the past, because now even these thyristor-based rectifier circuits are being replaced, and a lot of places they are already replaced by another family of rectifiers, which would be a discussion of our next chapter on the rectifiers. So let us focus on, in this chapter, which is chapter number 10, on the thyristor based rectifier, which gives us the controllable output voltage. So before we start, a small thing, it would be nice if you pause this video and you go back and watch video number 3.1, which was on power semiconductor devices, right? I think introduction. So there are multiple devices. Just review the thyristor, right? Just review the thyristor or silicon controlled rectifier, also known as silicon controlled rectifier. Just review this device from this video, and then you can come back and then continue watching the this particular video which we are doing now, right? Okay, now so thyristor circuit essentially looks like this, right? And what it does, is that if you draw the voltage versus current waveform, then in the on state, an ideal thyristor, or rather in general in the on state, the thyristor would be like this, right? Thyristor gets on. There are two conditions. One is that it should have a trigger, right? A gate trigger. So this is the gate. So it should have a gate trigger, and also it should have a positive applied voltage, right? So positive VT, right? So if you have a positive value of VT, that means you are inherently trying to forward bias the junction, PN junction, and plus you have a positive gate trigger or a gate trigger, then you can turn it on. And you cannot turn it off by removing the gate trigger. So it automatically turns off whenever the current becomes below the, right? So the off condition is whenever current becomes less than the holding current, right? More about this you can get in the above video. So now here we are talking about an ideal thyristor. So what we would assume is the holding current is 0. So if a thyristor is turned on, as long as it has a positive flow of current, the thyristor would continue to conduct even if you remove the gate trigger, and the thyristor would stop once you have 0 current flowing through the thyristor, right? So with that basic idea about the thyristor, let us start drawing the half controlled circuit, right? So now if you see, this was the full bridge single phase rectifier circuit, right? And then you have load here at the output, and input you have a AC source which is connected like this. So V in, right? Now what happens is, this is uncontrollable, so let us try to replace two diodes with the thyristor. So what I've done is I've replaced these two with thyristor T1, T2, and these two are diodes D1 and D2, right? And now let's see if I can manipulate the output voltage. For beginning, let me start with a simple example where we assume that the output is a pure resistive load, right? So let me draw the input voltage first, V in, right? And now let us say that I can give trigger to thyristors T1 and T2 at any instant. Let us say that I trigger T1 at alpha, right, at an angle of alpha, and I trigger thyristor T2 at an angle of pi plus alpha, right, where the alpha is defined with respect to the zero, which is the zero crossing of the input voltage, right? So I can, in this figure I can show you where essentially, let's say I'm assuming alpha, let's say this is alpha, right, then this is pi plus alpha, right, this is pi. So these are the instants where I'm triggering T1 and I'm triggering T2. Now, even though here I have shown only a single arrow, but then in real life we do not only give a single pulse to the thyristor. The reason being that the thyristor may not necessarily turn on, the pulse may not be sufficient. So usually you would like to flow the current, but if you flow continuous current in the gate of the thyristor, then you have additional losses. So as a trade-off, usually, although here we are representing it just by a symbol like this, in real life you give a trail of pulses to the gate for some time, right? So although we are showing it like this, the actual gate current is as shown below, or rather the actual gate voltage is as shown below, right? So this is how you actually trigger the thyristor, by providing a pulse train of currents, right, instead of a single pulse. But then in figure, as we move along, we'll only show a single trigger. Okay, now in this circuit we have shown the trigger points of T1 and T2. Let us continue drawing and let us see what will be the output voltage VO and what would be the output current IO, right, in this case. So again, let us start with the assumption that the initial condition, that initially current is 0. Here anyways there's no inductor, right? So initial condition is not required per se, but we can still, if you feel comfortable, we can start with that. So let's say this is IO, right, and here let me try to do what is VO. So initially current is 0. So you see thyristor 1 is not triggered. There is no device. T1, T2 both are not triggered. That means they cannot conduct. So they would behave as open circuit. So if you try to draw the equivalent circuit for the duration 0 to alpha, then you would see that both T1 and T2 are open, right? If both T1 and T2 are open, that means the positive terminal of the input supply is open. That means there cannot be any current that can flow through the input source, right? And the equivalent circuit looks something like this. This is open, and only through this diode this is connected and a resistance, right? So that means there would be no current flow in the resistance because there's no forcing function. There's no inductor also, so no current flowing through the resistance. So IO would be 0 and VO would also be 0, because in this case VO is nothing but IO into R. So till alpha, both IO and VO remains 0, right? Now what happens now, if you see at alpha, we are triggering to pulse to T1 thyristor. What is the voltage across T1? If I see VT1 now at alpha plus, if you see what is VT1, VT1 is nothing but at alpha just before triggering at alpha minus, right, just before triggering. If you see what is VT1, your terminal VT1 is your terminal voltage is, let's say, plus, right? This other thing is at a minus, right? Now if you imagine this path, right, if you imagine this path, then you can see that in this path the only device which is blocking this plus and minus voltage is VT1, right? Because there's no current, so voltage across resistance is 0. The diode D2 could have become forward bias if VT1 was not there, right? If thyristor 1 was a short, then diode D2 would immediately become forward bias. So D2 is not blocking the voltage, it is VT1 or thyristor 1 which is blocking the voltage in the forward direction. So that means VT1 is greater than 0, right? And therefore as soon as you give trigger pulse to T1, T1 would start conducting. Implies, so both conditions are met, VT1 is greater than 0, T1 is triggered, so T1 starts conducting, right? So as soon as T1 starts conducting, in the positive side, now you see once T1 is triggered, then it is as good as a diode. Why? Because as long as it will remain a positive current, it will flow. As soon as the current becomes 0, it will stop conducting. So now if you see the equivalent circuit, how does it look like? It would actually look like a 2 diode in a common cathode configuration, right? And therefore the one with higher anode, which is T1, would conduct and the other one would remain open circuit. So this is what will conduct, T1 will conduct, and this would be your circuit, right, on the top side. Now from the bottom, again you have two options. You have a thyristor T2 and you have a diode D2, right? You have a thyristor T2 which is connected here, and you have a diode D2 which is connected to this other terminal, right? Now from the bottom, which one would conduct, right? So since we are not giving a gate pulse to T2, you sort of understand that T2 will not conduct. But even if hypothetically, if we would have given gate pulse to T2 also along with T1, you see as soon as you give a trigger pulse to T2, then T2 is could be similar to a thyristor. Then there are two thyristors. It could be similar to a diode. Then there are two diodes in common cathode anode configuration. So the one with lesser cathode will conduct, and therefore D2 will conduct, and thyristor would anyways turn off. So whether you give only T1 or you give both T1 and T2, it would not matter. So the final circuit that you see here is something like this, right? This is the AC voltage going like this and then coming back like this. So the output voltage is equal to the input voltage in this duration, right? So the output voltage becomes equal to the input voltage, right, in this duration. And what about current? Current is here, it's pure resistance, so the current would nothing be but same as the output voltage wave shape, and the value would be divided by R, right? So alpha is the point at which T1 and T1 is triggered, right? Now what happens? Now you see current has become 0, right, at I0, and after I0, so the current has become 0, so T1 will turn off, right? T2 is anyways turned off because you gave a little bit of pulses, maybe up to 20 or 15 degrees or something like that, but then you remove the pulses, right? And so there is no device which is conducting because current has gone 0. So T1 is off, T2 is off. So again the circuit would look very similar to this first case. So going from pi to pi plus alpha, the circuit would be same as this, therefore no current, right, and therefore no voltage, output voltage. Again now at pi plus alpha, T2 is triggered, right? So now the bottom thyristor is triggered. So but then the input voltage polarity has also become negative. So now you can again do the analysis. You try to find the voltage across T2, at pi plus alpha minus, right? And then you would realize that we are giving triggering pulse, the voltage is positive, so T2 will start conducting, and from the top one you can see that D1 will conduct. So what you realize is that in this next phase your device T2 and D1 will conduct. In the first phase the device T1 and D2 conducts, right? And during this phase none of the device conducts. And again, when this starts, you would see that because it's a rectifier circuit, you would see the voltage would be nothing but negative of, so VO is negative of Vin in this duration, VO is equal to Vin in this duration, and the current would also be following the voltage, right? This is going to be the output voltage waveform and the output current waveform in case of half controlled asymmetric circuit, right? Why we call it asymmetric? We call it asymmetric because one of the leg is made up of diodes, 2 diodes, and the other leg is made up of 2 thyristors. So it's not symmetric. We call it asymmetric, and it's half controlled, you can understand, because there are 2 diodes and 2 thyristors, so therefore it is called as half controlled. If in subsequently we will see a circuit where you have all 4 thyristors, we will call it as a full controlled. Okay, with this basic understanding with the resistive load, let us try to draw the waveforms in case of a inductive load, right? So a load which is highly inductive. It could be a combination of R, L and E, right? Wherein L value is significant such that the load current is continuous, right? That is how we define. This is V in, right? And let's say now I have connected it to a load which is highly inductive, right? Which means that the output current is continuous. It may still have some ripple. You can consider ripple, you can probably assume that it is just DC. In either case, the output current is continuous because there is large value of L in the load. So now in this case where the load is highly inductive, let us try to draw the waveforms. Try to draw a bigger sinusoid. This is input voltage, right? Let us assume that the angle, the instance at which the thyristor T1 is triggered is alpha, right? And the angle at which T2 is triggered is pi plus alpha. Right, now let us see how would the output current and how would the output voltage look like. So here, since the load is highly inductive, so that means I0 is never equal to 0 in this full duration. So when we are starting at t equal to 0 plus, also current value is a positive value, I0 is positive, right? So at t equal to 0 plus instant, current would need some path to flow, T1 in T1 or D1, right? So current could be flowing from T1, current could be flowing from D1. current could be flowing from T1 depends on in the previous cycle what happened with T1, right? And similarly, current could be flowing from D1 depending again on what happened to T1 in the previous cycle. If let's say assume that T1 was on in this previous cycle for whatever reasons, right? Then T1 will continue to conduct, right? Because the voltage is positive, the cathode voltage is positive for T1 with respect to D1. But if in the previous cycle T1 was off and there is no gate pulse given, then T1 will not conduct. And therefore, in these circuits, usually it is better not to start drawing from zero, to start drawing from a decision making point, right? So here one of the decision making point is alpha. So you can start drawing from alpha, or you can very well start drawing from pi plus alpha also, which is a symmetric point. So here instead of starting drawing from zero, let us start drawing the waveforms from instant alpha. So what happens at alpha? At alpha, if you see, we are giving triggering pulse to T1, right? So among T1 and T2, among T1 and D1, which of the device will conduct? Now we have given a trigger pulse to T1, so T1 is now almost equal to a diode. So along with trigger pulse, if it sees a positive voltage, it will conduct. So now it only needs a positive voltage to conduct. Now between T1 and D1, you understand they are connected. Now D1 is sort of emulating a diode, and both the diodes are connected in the common cathode configuration. So whichever has the higher anode potential will conduct. In this case, T1 happens to be that device. So we can say that at alpha, starting from alpha, among the top two devices, T1 will conduct. Now among the bottom two devices, which device will conduct? T2 anyways, we are not providing triggering pulse, right? And therefore T2 will conduct. Even if we would have provided, as we saw in the previous case, that they are connected in the common anode configuration, and therefore the one with lesser cathode potential will conduct, and therefore T2 will conduct. So you see that in this first case, T1 and D2 will conduct. So you can imagine the waveform, this is how the current would flow like in this circuit, right? For this duration. So if this is how the current flows like, then what is output voltage? Output voltage, you can see Kirchhoff voltage law is equal to the input voltage. So let me draw the output voltage, which is same as the input voltage. And what about the output current? Output current anyways, now here we are saying it is an inductive, so we can assume that output current is anyways a constant for the full duration. We can more or less assume that. Okay. So I think it would be good if we instead of, we anyways know how the output current looks like, it is a DC current, right? So therefore it may be a good idea to, instead of drawing the output current, we can start drawing the input current. So in this case, the input current is same as the output current. Okay, so far so good. So from pi from alpha going till pi, nothing changes. So more or less same thing will happen. T1 and D2 will conduct, other devices would be reverse bias, and nothing would change. Now what happens at this instant pi? At this instant pi, so now among the bottom two devices, you see, you anyways are not giving a trigger pulse to T2. So among T2 versus D2, you realize that since you are not giving trigger pulse to T2, irrespective, so it would not behave like a diode, and therefore the only option for the current to flow through is D2. So D2 will conduct, right? So among the bottom, D2 will conduct. Now what about the top? You have two options, T1 versus D1. T1 was conducting just before pi, but at pi plus, what will happen at pi plus? The anode voltage of D1 will become higher than the anode voltage of T1, and therefore D1 will start conducting and not T1, right? Among the positive cycle, let me repeat it again, we have choice between T1 and D1. Now we have crossed pi, that means the input voltage has become negative. That means the diode D1 has a higher anode potential than T1, and therefore D1 will conduct, and because T1 current will be equal to 0, it will automatically stop conducting and it will turn off. So in this period, D1 and D2 conducts. So how would the current look like? So in this case, the output current only flows in this loop. It's almost like a freewheeling, right? There's no interference from the input. So the input current is 0, right? And what about the output voltage? The output voltage is the voltage drop across the two diodes. Assuming ideal diode, output voltage is also 0. Right? This is what happens in this period between pi to pi plus alpha. Now what happens at pi plus alpha? Right? Again, you see what happens between the top devices which will conduct and what happens between the bottom devices which will conduct. T1 anyways you are not giving trigger pulse, right? So D1 is conducting among top. Bottom, you can do the same analysis as we did for alpha. You would realize that T2 is the device which would actually conduct, right? So in this case, diode D1 and thyristor T2 conducts. So among the top it is D1 and bottom it is T2. And if that happens, then the current would, the DC current would flow through T2 and then come back through D1, right? This would be the direction of current flow, and therefore the input current will be equal to the negative of the output current, right? And therefore the input current would look like this. And during this period the voltage would be rectified waveform, negative of the input voltage, right? This will be your output voltage, and you can see that after this instant what happens at 2 pi. Again, you can analyze, you can see which top device will conduct, which will bottom will conduct. You would realize that after pi, again D1 D2 will conduct. What is after pi? That means after 0. So D1 D2 will conduct, the input current will be 0, right? And the input current will be 0 and the output voltage is also going to be 0.